Okay, so we finished with all the kind of sidestepping of background work that's going to be used now, and we're going to deep dive into SDC, or the synopsis design constraint. So how do we define a clock? A clock has to have a bunch of stuff about it. First of all, where does it come from? In other words, is it external? Does it come from an input port, either to the whole chip or to our specific design? Or for example, if we look at a chip, often a PLL, a phase lock loop, is what makes the clock. So the output of the phase lock loop would be the source of the clock. So we have to tell the tool where the clock actually starts so we can see where it dissipates to and what its sinks are. What are the different modules that receive that clock? What is the clock period? So obviously we have to tell it what that big T is, what the operating frequency is. And what is the duty cycle? We can also tell it. Usually we don't tell it because we don't usually care much about the falling edge of the clock if we're in a positive edge triggered design, and therefore we assume the default of a 50% duty cycle. So how we do that is with the create clock command. And this is the maybe most important command in SDC. Create clock. We want to tell it what the period is, so we do dash period, and this will be by default in nanoseconds, even though you can override that. We give it a name. This is some sort of a friendly name that we're going to use to discuss it. And if we do get clocks, for example, afterwards it will return us a collection that includes a clock named myClock. And we have to, without any dash, we have to give it the source of the clock. You cannot define a clock without the source. And the source of the clock is a port called CLK, and we'll get the collection of that by getPortsClock. Many of the tools will also accept it if we just wrote CLK, but it's more verbose to write getPortsClock inside square brackets like that. Okay, so that made this clock that has a 20 nanosecond period that came out of a port here that was called CLK. Okay, and we call this clock myClock. So that's our first SDC command. That's what it looks like. Question, can there be more than one clock in a design? Yes, of course there can, but you got to be really careful about clock domain crossing. We'll discuss it briefly. We can do a whole course just about clock domain crossing. There are tools for checking this and ensuring that you don't make things wrong happen. But one of the things that we do often find are generated clocks. So for example, if you take a clock and stick it into a clock divider, you have a clock that we know how it's made. It's all internal to our design. It's generated from the same clock. And to define a generated clock, we use the create generated clock command. It's kind of a similar type of a syntax to the create clock command. We give it some sort of a name, gen clock. We tell it what the source is. Okay, that's where the original clock comes from. We tell it what the division factor is. So this is divided by 2 clock, and we show what the pin where it disseminates from, similar to the source here of this guy. So that's a generated clock, and we can often have designs which have many generated clocks. So during synthesis, our clock is ideal. Remember, we don't have any skew. So we want to tell it that, listen, you don't have to go and stick the high fan out of the clock into your wired load model and get this large delay and this terrible transition. So what we'll do is we'll say set ideal network on the clock. For realistic timing, we should put some sort of transition, because if you remember, in our lib files, we have this table that says clock transition and net input transition and output load, and there are all these options here according to our lookup table, and for each of them we get some sort of a value somewhere around here, and we do some interpolation to find out what the actual TPD is, T rise and T fall of the output, even the power, and so forth. If we give it a 0, which is what set ideal network is doing, we're somewhere that's out of table. Since this is a nonlinear delay model, all of the types of them are, bringing something that's out of table is really bad. It's very unrealistic. So we want to give it some sort of a value that is at least inside the table, so the rest of the design works in a normal type of functional way. So what we would do is we would say set clock transition, give it some sort of transition, so the clock, instead of looking like this, will look like this. And that way, when we take our flip-flop and we look at the transition that goes into the rising edge of the flip-flop, we have something here, in this case 0.2, and we can go and find where 0.2 is on our T-rise in our table and not have something that's out of table over here. Okay, we might also want to add some jitter. So jitter we'll talk about later, but if we want some sort of jitter, we define that as clock uncertainty. That's part of our delta margin that we showed before. Okay, so we say set clock uncertainty 0.2. We can add it to hold and set up separately by adding something like minus setup. So that's an option to do, is add uncertainty to our clock. And finally, I just want to note that after building a clock tree, we don't want the clock to be ideal anymore. We want it to have real delays and real transitions, and so we would use this set propagated clock. On the tools nowadays, often they are able to tell that there was a clock tree built after clock tree synthesis, and therefore we won't actually need to add this command into the SDC or provide a separate SDC after clock tree synthesis. But there is such a command. Don't usually use it during synthesis because it can cause strange things to happen. Okay, so that was discussing our clock. There are other things. There are books about SDC. We could talk about it for hours, but that's the basic clock definitions. Now let's go into IOs. So as we discussed before, there are different types of paths. There's a reg-to-reg path, inter-reg path, reg-to-out path, and into-out paths. For a reg-to-reg path, defining the clock basically gives us all we need to know. But for an inter-reg path, a reg-to-out path, and into-out path, we have what is happening outside the chip, this guy, and this guy, that we have no idea about. We don't know where the actual flip-flop is or what type it is, what its setup time, etc. is. We don't know what the delay to the flip-flop is, and we don't know anything about the clock skew that gets to the position here. We know that there has to be something that uses this data that we pushed out of our block somewhere, and we can assume it's some sort of a synchronous flip-flop or something, but we have no idea about it. And if we have no idea about it, we can never meet any type of, or define any type of max and min delay on such a path, or similarly on such a path. So what we have to do is we have to make some sort of a model for this. Okay, so the first way, the traditional way, I guess, to do it is setting an input and output delay. So if we would know that the delay over here, the arrival time at this node is, say, 0.8 nanoseconds, right? Then we could give what we call an input delay and say it took 0.8 nanoseconds from the rising edge of a clock that is the same clock that reaches this point. Similar here, if we say that it took from the output of here, it took to get to D over here, let's say it took 2.5 nanoseconds for the example I'm going to show, then we would say there's 2.5 nanoseconds delay on this path with the same clock clocking the output. So how we would show that is set input delay 0.8, that's saying this guy here is 0.8 nanoseconds, minus clock, it's from the same clock that reaches here, the same clock that we gave it a name CLK, and we're going to define this thing perhaps on all of the inputs to design. So we would do it on all inputs, but we don't want to define it on the clock input because that would be very strange. So we do remove from collection. We remove from all inputs the input that's called clock. So it puts it on all of the inputs except for the input clock. Similarly, for the output delay, we would say set output delay 2.5 nanoseconds from that's relative to this clock, and we're going to put it on all of the outputs of the design. There is a better methodology that's called a virtual clock. Let's not confuse you too much at this point. I'll get back to that. This is very confusing and problematic, anything to do with these I/O constraints. In fact, what I'm going to show you now is a different approach to I/O constraints, and that's with using a command called set max delay. So a max delay is not looking at all at a synchronous type of a clock sort of a definition. It's just looking at the delay between 2 points in a design. Sometimes, and we will discuss a bit later why we want to look at max delays rather than looking at input and output delays. So what I can do is, for example, do set max delay, some sort of number, 5 nanoseconds, minus from all of the inputs except for clock. What will that do? So we have our design here, and we have our clock input here, that our clock input goes to some sort of a flip-flop, right? And we have some sort of an input here, let's say A, and it goes through some sort of a delay over to here. What set max delay is, it says, listen, this will take 5 nanoseconds. Has nothing to do with any of the skew on the clock where it rises or falls. Why that can be better is because we have no clue what the skew or anything was on this clock, and we were assuming it has to do with this clock. This just says, listen, let's just constrain that to 5 nanoseconds. And we'll see why that's very important later on in the course. Okay, similar, we can say set max delay 5 to all outputs. So we have our thing here, and here's our some sort of an output, right? So it says set max delay. That means from clock. Remember, this is the whole launch path. That should take no more than 5 nanoseconds. It would be better to make it from the Q of the flip-flop to out, but that's a possibility. Okay, additional, we must model the transitions on the inputs. So one of the things here is, what is the transition of this node A here, right? Is it something that goes up? Ideally, that brings us to the same problem with the out of table. So it would be much better, for example, to say that assume, to make it relative to our technology, that there's some sort of inverter here that's actually driving this, which will give it a more realistic type of a waveform. And so what we can do is set driving cells, say what the cell that drives all these inputs is. It says it gets from the library. Get lib cells is one of these get commands that looks for things in libraries. Mylib, that's the name of my library here. Inv4, that's some sort of a inverter inside my library. And it says take the Z pin, the output pin of that. It says, okay, listen, this guy is the guy who's driving my inputs. And that gives a more realistic type of a look. Again, we would do it on all of the inputs except for clock. In fact, it's very important to model what the thing is here. We can also go and say what the input transition is on this instead of putting a driving cell, but it would be better to put a driving cell over there instead of an ideal type of a ramp. Similarly, when we have some sort of a, so at our output of our design, we had this flip-flop, it drove some sort of a cloud. There was some sort of a gate here that reached this output called out. But what is out here? We don't know. So if there's nothing, if the capacitance is 0, then this guy would be working too fast and so forth. We could put a minimum size inverter or something here. So we better model some sort of load here. What is this load? Well, we'll just use some sort of load. We'll say, for example, we can take an inverter from our library, look at what the input is of it, and set that on all the outputs, and that will model this type of a load. So it's very important to model our outputs. Okay, to summarize our constraints, let's look at it again. So this is our design. These reg-to-reg paths, they're completely enveloped inside our design, but these into-reg paths and reg-to-out paths and the into-out paths as well, they need to have the part that's missing modeled in order for us to apply our static timing analysis to them. So what we do is we do something like an input constraint, an input delay to model this guy, an output delay to model this guy. In addition to that, we have to show what our driver is here. So that's like our set driving cell, and we have to show what our output load is, and so that's with the set load. So that's how we're going to model our inputs and outputs to our design. Next, the next category that we're going to discuss is timing exceptions, and there are several types of timing exceptions that we have to define for the STA. One of those, for example, is the topology of the network we saw earlier, and if you remember, we had this type of a path that was non-existent, right? Because we could, if we had 0 here, we have 1 here, so we cannot go through that type of a path, and the same for this side. So if we want to define such a thing, what we have to do is we have to define these two paths as a false path. How do we do that? Well, we use from, through, and to. Okay, so from our start points, to our endpoints, and through are any internal pins that we have in the design. So how would we do that? We would say set false path. That's our SDC command, minus through, because we don't have to say from to define this path. All we have to say is that it goes both through this and this. So we say get pins mux 1, pin I0, and minus through get pins mux 2, pin I0. Similarly, we should set a false path that goes through mux 1, pin I1, and mux 2, pin I1. So that would set a false path there, and we wouldn't have a problem that this could be potentially become our worst negative slack. In fact, we won't even check that timing path. Another type of false path that is very commonly seen is a clock synchronizer. So a synchronizer is just a shift register. It's this type of thing with usually 2 flip-flops. It can be made sometimes with more of them. And it's clocked by this C2, which is a second clock. This is driven by paths that are clocked by flip-flops that get a different clock. So we have a clock domain crossing, which is something that is illegal to do. I will give a short overview of synchronizers later on in the course, but in general, we are not allowed ever to take one clock and talk to another clock, to have a launch path on one clock and a capture clock on the other clock. This will always be a timing violation. A synchronizer is used where we know that this is a possible thing to do by design, and obviously this path is very problematic because it can never meet timing. So what we have to do is define it as false path. So how we would do that is set false path minus from flip-flop 1 CP, this would be called CP, to flip-flop 2 D. That means this is a false path, it won't check timing on it, and we won't get any violations. In an alternative way, we can just say, listen, we know by design, and we checked it very well, and we used a clock domain crossing tool to check that we don't have any of these types of violations that we didn't know about. We can say, listen, set type of a global false path between all of the things that are on clock 1 and clock 2. Better than setting such a global false path, what we should do is say set clock groups minus logically exclusive minus group get clock C1 minus group get clock C2, and that will remove all of the paths that go through clock 1 and clock 2. So that's another type of a SDC command that we could use. There is a third type of a thing here where we might be, for instance, going from a fast clock to a slow clock, or a slow clock to a fast clock, and by design it's supposed to work, and such a path is supposed to, for example, take 2 clock cycles. So we have this flip-flop that's driving another flip-flop, and we know that the delay here will take 2 clock cycles. So this is our launch edge, and this is our capture edge, and we want to tell the tool how to do that. What we're going to do is use a command called set multi-cycle path. So set multi-cycle path from flip-flop 1 CP to flip-flop 2 D, right? That's what we wanted to do. And we say that it will take 2 clock cycles. But look here, we said that's minus setup. So that's a multi-cycle path only for setup or max delay checks. The way that multi-cycle path is defined, and you can Google it and read about it, is that if we would do that, we'd probably get hold violations in other places. So we have to define set multi-cycle path minus hold, where we put our multiplier of the cycles as 1 less than the multiplier of this. So if this was 10, this would be 9, for example. If you don't do that, you're going to get all kinds of strange hold situations. Again, you're invited to go and Google it and understand why, but I think that for a basic thing, just remember that rule. Every time you write a set multi-cycle path minus setup, add a minus hold. That is 1 multiplier less. Okay, finally we can discuss case analysis, which is a special command that defines constants in our design. Okay, so there are many designs, many values in a design that can assume to be constants. For example, if we're going to write a register, write a certain value at startup, and then in this operating mode it will be constant, or we're going to hold an external pin or something like that at a constant value. What we want to do is we want to make sure that this constant is propagated through the tool. For example, if we have an AND gate when one of the inputs is a 0, we know that the output is a 0 regardless of what is here, right? So we don't want to have this as any timing path because it's constantly a 0. It doesn't matter how this rises and falls. This is not going to change, so it's actually a false path. To do that, it's called constant propagation. So if we define this pin as a 0, it's going to propagate the constant and basically set false paths on all of these other paths that go through design. Okay, that is done with a case analysis. So to propagate the case analysis, we use a set case analysis command. So set case analysis 0, and we say, for example, get ports test mode. So this is telling us that we are not in test mode in our SDC. We're going to set a case analysis 0 on the port called test mode. Okay. Design rule violations. This is the last category, basically, of SDC commands that we're going to be discussing. I think that covers all of them. There may be all kinds of corner cases that are strange SDC commands that you probably will never use, but you can look up these things up in a book. For now, this is the last category we're going to discuss. So design rules, we can either define this inside our synthesis and place and route tool, or we can define it through SDC commands. And So we have three types of major design rule violations. One is the transition of a net. So we can write set max transition and give it some number in nanoseconds, and that will check, the tool will check that no net has a larger transition, a T-rise or a T-fall, above this constraint. You can do set mid transition as well. Maximum capacitance, so you would do set max capacitance and say what the maximum capacitance is. Now, these two definitions are ultra important, and the reason again being our lib file that has our T-rise and our C load, and it has a set of values. And remember, to be inside the table, which is extremely important because we don't know what's going on over here or over here or over here or over here, we have to have all of our values of transitions and capacitances inside the table. So you want to set a min and max capacitance in the ranges that are defined in these tables, and you can do that through SDC. Usually the tools will actually read these from the lib files, but if you want to override what the default from the lib file is, you can do it through these SDC commands. You can also define a max fan out of a gate. That just says, okay, we have some inverter. Don't let this inverter have more than a fan out of 20. So you'd say set max fan out 20 or something like that. It's not something that usually is a straightforward constraint. More like a max capacitance would be the constraint, but it's something that kind of as a rule of thumb, we may want to keep such a max fan out. A final point about at least constraints and so forth. So we have something called yield-driven approaches and advanced static timing analysis. There are many concepts, approaches, terminologies, and all kinds of things that are used in timing analysis to achieve high yield sign-off. For example, on-chip variation, or OCV, advanced on-chip variation, AOCV, even have parametric on-chip variation, POCV, signal integrity, and there are many more. In fact, I put a little asterisk here that said that between the time I wrote this slide and presented it to you, each EDA vendor has presented another method for timing closure that you just must know about and you have to use, or else your chip is not going to work. Okay, that is obviously cynical, but it's true. We get at every SNUG and at every CDN Live new types of OCV and new types of timing constraints that are presented. Okay, so we'll discuss this in the future, but these are these parts of the delta margin that we discussed before. They will fill up our delta margin. The harder usually we make it to close timing, then somebody will come up with another thing that will remove a bit of our constraint. Okay, that was just kind of a cynical remark about that, but there are many more things that today are used, and some of them are really important.